Let's start talking about permutation groups. We have seen the definition before when we were giving examples of groups, but here it is again. Let A be a set, any set whatsoever, then perm of A is the set of all bijections from A to A. Means an element of the set perm of A is a one-to-one and on-to function from A to A. And this set, which I'm calling G here, becomes a group where the group operation is composition of functions. The inverse of an element is the inverse function, and the identity of the group is the identity function. So if you give me two elements of G, sigma and tau, there is a thing called their composition, their product, which is written sigma compose tau. And what is it? Well, tau is a one-to-one onto function from A to A. Sigma is another one-to-one function from A to A. So you can apply them back to back, and the net result is going to be a new one-to-one onto function from A to A, which we write like this: first tau, then sigma. A tau followed by sigma. You see, you have to read it from right to left, because when you apply it to an element, tau gets applied first. It's sigma of tau of A. Yeah. So that's a new bijection from A to A, and that's the product in this group perm of A. Okay, and the inverse element is just the inverse function. Okay. That's the permutation group of a set. The book uses the notation ought of A, means the same thing. In particular, when you have the set 1, 2, 3 up to n, if that's your A, then the permutations of that set is denoted by S sub n. This is called the symmetric group of n letters. Symmetric group on n letters. 1, 2, 3 up to n. And I want to go through this theorem of Cayley. Says that any group A is isomorphic to a subgroup of perm of A. So if A is a group, A is after all a set with some operation, but it's a set. So you can consider this new group perm of that set, so set of all bijections from that set to itself. And A can be identified with a subgroup of this group perm of A. Note that perm of A is much, much bigger usually than A. Okay, so if A has 5 things, then perm of A has 5 factorial things, because there are 5 factorial bijections from a set of size 5 to itself. However, you can identify it in there. In particular, if you have a finite group, then it's isomorphic to a subgroup of one of these symmetric groups. But this sort of tells you how important these permutation groups are. Tells you that, for example, if you're only interested in finite groups, then if you just look at subgroups of Sn contains isomorphism types of all finite groups. So take any finite group whatsoever, there is some subgroup of Sn which is isomorphic to one of these, to that one. Yeah, so if you just look at subgroups of Sn, all types of finite groups show up. So that's why they are very, very rich, and they are very, very important. So we'll study them in detail next. Okay. So this theorem is an advertisement of the importance of symmetric groups. Okay. So to prove this, we need to look at these bijections from A to A. You see, what I need to do is I need to define a function from A to perm A. I have to show that A is isomorphic to a subgroup of perm A. So I need to give a function from A to perm A. So you give me an element of capital A, and I have to give you an element of perm A, which is a bijection from A to A. So I have to define a bijection from A to A that depends on A, and here it is. And we'll use this time and again, so let's study them separately. So let A be a group and fix an element little a in capital A. And then you define a function L sub A from capital A to itself simply by L sub A of x is A times x for all x in A. So what this function does is it takes an element of capital A and multiplies on the left by A. It's called the left multiplication by little a. So this capital L stands for left multiplication. I want to verify three little things about this function. That L sub E is identity, that's the first one. How do you check two functions are equal? Well, you take some element of A and apply both sides and see you get the same thing. L sub E x, it means E times x, which is the identity function applied to x. So this function and that function takes the same value on every input, so they are the same. Very simple. 2. To check L sub A circle L sub B is L sub AB. L sub A circle L sub B applied to some x in A gives you what? L sub A bx. That's L sub B applied to x. That's same as A times bx. By associativity, that's same as AB x, but that's same as L sub AB applied to x. Again, this function and that function takes the same value on every input, so they are the same. 3. I want to check that the inverse of this function L sub A is the function left multiplication by A inverse. So here the whole A inverse is in the subscript. So let's compose L sub A and L sub A inverse and see what we get. Well, by 2, you get L of the product. But A times A inverse is identity, so L sub identity. But we just checked that L sub identity is the identity function. And you can verify that if you compose them in the other order, like this one first and then that one, you also get the identity. Verify this. Same verification. But this tells you that this function and that function composed together gives you the identity function and in either order. But that exactly means that this guy is the inverse of that guy. That's what inverse functions mean. So that's why 3 is true. Now that we are armed with 1, 2, and 3, we can prove part A pretty quickly. So here's a sketch of proof of part A. So let's define a function called lambda from A to perm A by lambda of A equal to L sub A for all A in A. Note that our exercise part C or part 3 says that indeed each of these things are 1 to 1 and onto, because I found the inverse, you see. The inverse of L sub A is L sub A inverse, so in particular L sub A, so each L sub A is a bijection from A to A. So they are elements of perm A. So indeed this lambda is a function from A to perm A. And then 2 says what? Says that lambda is a homomorphism. That lambda of AB is L sub AB, but that's by 2 L sub A circle L sub B, but that's lambda A circle lambda B. So lambda of AB is lambda A times lambda of B. This times is the multiplication in the group A, and this dot is the little circle which is the multiplication in perm A. But this says, so lambda is a group homomorphism. Now I want to check that it's a injective homomorphism, it's 1 to 1. And we know how to do that. We have to check that the kernel is trivial. So suppose A is in A such that lambda of A is the identity element. That's the identity of this group. So this is assuming that A is in the kernel of lambda. And then you want to check that A is actually the identity element of A. But what does this mean? Lambda AX, which is L sub AX, is same as identity applied to X, which is just X. On the other hand, this is AX, and this is for all X. So in particular, A times identity is identity. It holds for all X, so it holds for identity. But this is A, so A is identity. So this tells you that if something goes to identity, it was identity to begin with. So the kernel of this map is just the identity element, identity of A. So lambda is injective. And now that you know that lambda is injective, consider the map lambda as a function from A to the image. By that I mean lambda of A, which is now, I know, a subgroup of perm of A, because we proved that the image of a group under a homomorphism is a group on the right hand side. Well, it was left as an exercise, I suppose, but we stated this theorem. Yeah, so M lambda is a subgroup of perm A, and lambda defines an isomorphism from A to this guy. So A is isomorphic to a subgroup of perm A. That's part A, and part B now follows immediately using this exercise. And this is very intuitive. It says if two sets are in bijection, then their permutation groups are isomorphic. If you can match up the elements of two sets, then permutations of one set defines you permutation of the second set, and this becomes a bijection. So this I'll leave for now. We'll do it next time. But if you grant me that, then now let G be a group, finite group, and let n be the number of elements of G. And I want to show that G is isomorphic to some subgroup of some Sn. I'm going to take this n being the size of G. Then G, there is a bijection from, there's a bijection from G to the set 1, 2, up to n. Well, this is essentially saying that G has n elements. If you have n elements, you can match them up with 1, 2, 3, 4, up to n, and you have a bijection from G to this set. But then by exercise on the right, perm of G is isomorphic to perm of 1, 2, n, which is what we call Sn. And by part A, G is isomorphic to a subgroup of perm G, and perm G is now isomorphic to Sn. Oops. So G is isomorphic to a subgroup of Sn. That shows permutation groups are extremely important, so next time we'll study them in detail.